Okay, this presentation is going to be on a closed loop control scheme for implementing a switching technique known as split phase switching. Now, split phase switching has begun to find use in a number of hybrid switched capacitor power converters ever since its introduction at the COMPEL conference back in 2014. Now, this technique was first demonstrated using the two-phase Dixon converter, whose equivalent switching states are shown here on the left. Now, the idea here is that as we transition from phase 1 into phase 2, we are abruptly connecting two capacitor branches in parallel, highlighted here as the blue and red branches. Now, at this moment, these branches may or may not be holding the same voltage, particularly when you start accounting for large voltage ripple on your flying capacitors. Now, since branches in parallel must hold the same voltage, any voltage difference come the start of phase 2 will result in a rapid redistribution of charge, or a transient current spike. Now, to visualize this, we can plot voltage stored on each branch versus time, where here on the top right, you can see that come phase 2, these branches do indeed hold different voltage potentials. Now, subsequently, the circuit attempts to instantaneously violate Kirchhoff's voltage law, and a large current pulse occurs. Now, this rapid redistribution of charge is referred to as hard charging loss, and is the loss mechanism behind this slow switching limit, if that's a term you're familiar with. Now, what split phase switching does is to strategically partition a phase into two or more segments so that hard charging losses can be avoided, thereby realizing soft charging. So what we're doing here is splitting phase 2 into subphases A and B, where in this case, as phase 2 begins, the blue branch is disconnected. Now, this allows the red branch to discharge into the load independently, but as soon as both branches are holding equal voltage, then the blue branch is introduced in phase 2B, where both branches now conduct together for the rest of the phase. Now, as a result, there are no longer any current spikes because any voltage discontinuities have been fully avoided. Now, one important thing to note is that the timing of this split phase transition is critical to its effectiveness. Now, for example, if we were to transition to phase B too late, hard charging losses will be introduced, and likewise if we were to transition too early, as shown here. Now, there have been a handful of works providing detailed analysis on what these appropriate timings are. However, while this analysis is helpful with design, it's not immune to parasitic influences and component tolerances and mismatch. So to make split phase switching a practical reality, what we really require is a closed loop control scheme that can converge upon the correct timings automatically. But before we get into designing our controller, I'd like to point out that the benefits of split phase switching are certainly not limited to just the Dixon converter. In fact, split phase switching has been used in a growing number of converter topologies which would otherwise not have been considered quite as competitive. Now, among these, several come with inherent PWM regulation capability, which makes this technique highly relevant for point-of-load applications, for example. Now, one topology not shown here is the Symmetric dual inductor hybrid, or SDIH converter, which is the converter that we'll be using as an example for the rest of this presentation. Now, this is an excellent topology that's closely related to both the series capacitor buck converter and the dual inductor hybrid, which is its single-ended cousin. However, the SDIH uses fewer components to provide an interleaved high-side port, which reduces filtering requirements. It also has a uniform current distribution as a result of its complete symmetry, which can assist with practical component selection. And last, it requires only two inductors for any order of switched capacitor network. Now, this converter operates with two primary phases. However, two additional phases, shown here as phases 2 and 4, are typically inserted to enable voltage regulation. Now, as is, there is a problem with this phase arrangement. Now, similar to the Dixon converter shown earlier, during phases 1 and 3, there are a number of voltage loops which introduce hard charging loss if not addressed. Now, for example, it turns out that the voltage loop I'm highlighting here cannot satisfy its listed KVL equality come the start of phase 3 because the voltage along the red highlighted branch will not equal the voltage along the blue highlighted branch. Now, fortunately, this can be resolved using split phase switching. Now, how we do this is a little bit different than before, but under the assumption that all capacitors are equal in value, then what we can do is split both phases 1 and 3 into sub-phases A and B, as shown. Now, to understand this, let's now take a look at some time domain waveforms where we're going to focus in on this highlighted voltage loop that's formed during phase 3A as an example. Now first, if we plot the switched nodes of each output inductor, you'll see chopped voltage waveforms whose duty cycles can be varied between 0 and 50% for effective output voltage regulation. Now since these waveforms are offset by 180 degrees, we get interleaved current waveforms for reduced output ripple. Now next, we're also going to plot the 3 voltage waveforms that are going to tell us whether or not that voltage loop has been satisfied come the start of phase 3A. Now if we do our split phase timing correctly, then we should be able to satisfy this constraint without causing any hard charging loss. Now since we're trying to equate both sides of this equation, we can also plot the difference between VL2 and VR1. And at this point, we don't need to consider the switch node voltages or inductor current waveforms, so we can remove those. And instead, we can plot the current flowing through capacitor CL1, where this is going to help us visualize any hard charging loss as before. Okay. So let's step through the phase sequence, starting with phase 1A. On the left here, I'm highlighting charge flow in the converter, and looking at the waveforms on the right, we see capacitors CL1 and CL2 increasing in voltage as they absorb charge, while capacitor CR1 decreases. Now, if we time our phase transition just right and transition to phase 1B right as our equality is satisfied, then both these waveforms will rise together during phase 1B, before leveling out during phase 2. Now, one thing to point out here is that since none of the capacitors conduct any charge during phase 2, they simply hold a constant voltage for the duration of that phase. Now we have arrived at this critical transition to phase 3A. Where the highlighted voltage loop is abruptly engaged. Now, fortunately, in this case, both of our branches are holding equal voltages, and so our equality is satisfied at this time. And so there's no hard charging loss, and the capacitors smoothly dock into their new phase configuration without any abrupt changes. However, I will point out again that if we had not transitioned from 1A to 1B at the correct time, then this equality would not hold, and we would again incur transient current spikes throughout our power stage. Now here I'm showing a scenario in which we transition from phase 1A to 1B far too early and before our soft charging conditions had been met. So subsequently come phase 3A, this voltage discontinuity causes hard charging losses, and each of our capacitors are abruptly rebiased to satisfy KVL. So how do we use these insights to develop a controller? A controller that can actively converge on appropriate timings and that is immune to variations in load, current ripple, voltage ripple, and operating point. Well, to do so, one approach is to rewind to our phase 2, where I had mentioned that the voltages stored on each of our capacitors was static and unchanging for the duration of this phase. Now, this presents an excellent opportunity to measure these voltages before our voltage loop is implemented in phase 3A. That is, we can determine whether or not our equality will be satisfied before the voltage loop itself is implemented. We can then use this information as feedback to modify our phase timings come the subsequent switching period. Now, there are a couple of additional things that are very attractive about taking measurements during phase 2. First of all, since we have a long time interval within which to take these static measurements, we have greatly relaxed the bandwidth requirements on our measurement circuitry. Second, as is typical in a standard buck converter, phase 2 begins under zero voltage switching conditions, meaning that there will be very little switching noise within the converter at this time, which could otherwise corrupt our measurements. And third, the bottom plate of each capacitor is already connected to ground, which means that we can take single-ended voltage measurements rather than having to deal with differential signals. Now, while a typical approach to taking these measurements might be to have any number of ADCs before computing this equality digitally, here it's also appropriate to use a much more simple or perhaps even elegant solution, that is, a low-cost analog front end, where in this case, when the op-amp's output is equal to 0 volts, our equation has been satisfied. Now, you could certainly then run the signal into a standard PID type controller, but keeping with simplicity, here we chose to implement a 1-bit hysteretic controller, or a higher-lower type convergence algorithm. Now, before we proceed, I'd just like to point out that resonant switched capacitor converters typically do not have this quiet regulation phase, and so have to use other methods to perform the sensing. So if you'd like to see an alternative solution to what we're doing here that is applicable to resonant converters, our group has another presentation on that subject. But for our regulating converter, this solution works very well. So let's now take a look at the resulting system. First of all, we built a 6th order SDIH converter designed to operate with a 48-volt input and a regulated output of 3.3 volts, with components listed on the top right here. Now, taking this converter, we then hooked it up to an FPGA, which is used as our clock generator in this case, but this could be an ASIC or whatever you prefer to generate your clock signals. We then tap out the 3 voltage waveforms and route them around to our split phase controller front end, which was built on a separate daughter board. Now here I've made a few circuit modifications to allow us to compare about mid-rail, which just relaxes our common mode input range, but the idea here is the same, and you can still make out the desired expression in its transfer function. So next, we take our controller's output and feed that back into our FPGA as a feedback signal that's used to adjust our split phase timings, thereby closing the loop. And finally, we also tap out our converter's output voltage and wrap that around to form a similar 1-bit voltage regulator. Okay. So before showing you this control scheme in action, first I'd like to show you some measured results obtained when split phase switching is disabled. In other words, we're going to begin by temporarily removing the split phases and returning to the initial problematic 4-phase configuration. Now, since in this case there is no split phase, we miss our crossover point, and come phase 2, our equality is not satisfied with a fairly large difference between the red and blue curves. Now, subsequently, come phase 3 and the formation of our voltage loop, there is a rapid redistribution of charge as both circuit branches are forcibly clamped together. Now, at the same time, each of our flying capacitors sees a step change in voltage, implying very large current spikes and hard charging loss. Now, next, if we re-enable our split phase controller and introduce the split phase clocking scheme, things look very different. Now here our controller accurately converges on a timing scheme that transitions to phase 1B as soon as our equality is satisfied. So when we arrive at phase 3A, there is no instantaneous voltage jump, and our capacitors experience smooth and continuous voltage transitions, which is a definitive indication of complete soft charging. Now, while we've only focused on one voltage loop, this soft charging behavior is not confined to just these capacitors. If we plot all of the right-sided capacitor waveforms, we see that this behavior is consistent throughout the entire network, where again, active split phase control ensures smooth, continuous voltage waveforms across all flying capacitors with no abrupt voltage steps. But does this really make much of a difference? Well, it turns out that it does. Taking a look at the converter's efficiency, we see that with split phase control disabled, our heavy load efficiency is less than 85% as hard charging loss worsens with increased capacitor ripple at heavy load. However, when closed loop split phase control is enabled, we see up to a 40% reduction in total converter losses, where optimal phase timings were actively tracked for each of these measured data points. Now, finally, we can also compare this to the result obtained when using calculated split phase timings, where these calculations assume small inductor current ripple as part of their derivation. Now, because of the small ripple assumption, the calculated timings do not accurately capture the split phase requirements at light load, where at light load, inductor current ripple is very large with respect to DC offset. Now, as a result, the calculated timings can actually perform worse than if no split phase control were used to begin with, which just serves to further motivate the use of an active split phase control loop. So to summarize, I've described complete soft charging within a hybrid switched capacitor structure using this concept of split phase switching. Then, using the SDIH topology as a case study, we applied this concept to the design of a split phase control scheme where we were able to capitalize on the quiet regulation phases, which allowed us to use a low-cost analog front end. Finally, the resulting system was used to demonstrate this technique's effectiveness in elevating a topology's performance. And that's it. So thank you for listening.